Hi, welcome to PyCon Canada. Thanks everybody for coming. And I'm Jessitron, and I'm here to tell you that Git happens. Now, Git happens because version control is essential for any software project, no matter what language you develop in. Our code, it's not just one static bunch of text files. It's the sum of all our additions and changes over time. And Git is the best version control system because it helps us express that history vividly. So, Git gives us three things that are essential to our project. One is reproducibility, which is really important in science, but also in any production software. Two is collaboration, because working with a team is the hardest part of programming, and Git can help with that. And finally, something that most other version control systems don't do as well as Git is experimentation. If I could have one superpower, I think the ultimate superpower would be saving my game. If I could go back to another point in life, an earlier point, and then try something again and see what happens, that would rock. And that's exactly what we have in Git with our work. We have infinite saved game slots. So I'll talk more about that in a minute. It's pretty obvious that I think Git is awesome. It's the best version control system we have. And it's really awesome to learn about because it's based on a couple concepts that are really beautiful and elegant and combine to give us speed and efficiency and power to experiment. But Git is also terrible because the API is inconsistent and confusing. And because those amazing, cool concepts are not ones that everybody already knows. So until you know them, they get in the way. Git is awesome because the documentation is fantastic. The documentation in the help pages is super detailed and thorough. And of course, there's websites everywhere that will teach you what to type in Git. But Git is terrible because that elaborate, elegant documentation is written in a secret language with all kinds of vocabulary that normal human beings don't yet know. When I was preparing this talk, I printed out the help page for Rebase, and I started circling all the words that are specific to Git that I didn't quite understand completely. And at 75, I said, this is ridiculous, and stopped. So in this talk, I'm going to give you those concepts, those elegant concepts that once you understand them really give you the keys to the power of Git, and vocabulary, the secret words that show up all over the help pages and the internet so that you can talk about Git and know what to Google. And finally, I'm going to talk about the motivation behind Git because I think a lot of us have experienced, I certainly have, the problem that Git is harder than other version control systems. There's more to type, that confusing interface, but we put up with that because it gives us great power. So I'll talk about why you would use Git and the benefits we get. What I won't talk about is what to type, because you can get that anywhere on the internet. There's lots of sites that tell you what to type, but not what's going on when you type that. And finally, GitHub is really cool, but it's out of scope. I'm talking here about how to use Git locally on your computer and how to collaborate with your team. All of that applies to GitHub, but we got to start here first. This is the really interesting part to understand. All right, step one, accept that Git is hard. If this is the part of your brain that thinks about version control on Subversion or Mercurial or whatever your favorite version control system is, you need about this much of your brain when you're using Git. That's because Git is much more powerful than other version control systems, and with great power comes great responsibility. So just accept that we're going to need to use more of our brains, and I'll tell you what we're going to get from that. What we're going to get from that is to tell the story of our project. Git lets us put meaning into our project history. So say you want to document your day, and you give your little brother one of those big old VHS video cameras, and he carries it around on his shoulder. He's 8, so it's bigger than he is, all day, and he follows you around. And at the end of the day, you pop the cassette out of that video camera, and you say, here it is. This is my day. That's your project on Subversion, most other version control systems. Or you could take one of those little digital cameras, give it to your best friend, and he follows you around all day, watching in the preview screen to see what you're going to do. And then at the end of the day, he uploads it to his Mac, loads it up in iMovie, slices and dices and rearranges it to make a coherent story, narrows it down to 3 minutes, puts it to music, and uploads it to YouTube. That's your project history on Git, if you choose to write it that way. It's more work, it takes more thought to really tell the story than to just say, well, this is exactly what happened. Okay, so that's some of the power that we get from Git. And I want to tell you about the day that I accepted that Git is hard and just dealt with it, and how that's changed my life. And obviously, it's changed my life, or I wouldn't be here today. So one day on my first project that I used Git, I had made a commit, and then I was like, oh, I wish I hadn't made this on the master branch, because this is not mainline. I wish I had made a feature branch first so that I could go back to master and fix a bug. And I knew that Git is awesome and would totally do that. But Git is also terrible, because I went to Google and I tried to figure out how to do that, and eventually, like half an hour later, I had 6 lines that I could type, and that was the magic spell to do what I wanted to do. And yes, it did that, but I had no idea what the words I was typing meant. And so the next time I hit a problem like that, I said, stop. I don't like magic. I like technology. It's magic when you don't know how it works, and it's technology when you do. And one of these we can manipulate to our advantage. So I said, okay, I'm going to figure out how this works. And I spent about 4 or 6 hours, somewhere in there, hopping around the internet, reading about the concepts inside Git, watched one video, and after that I said, oh, now I get it. And it's actually 2 commands, and I know exactly what I'm typing and why. So I'm going to take that 4 to 6 hours, and you guys get that in 40 minutes. And at the end of this talk, you won't necessarily know what to type, but you know what to Google to find out what to type, and you'll be able to read the page that comes back to you. All right. So now let's talk about what makes Git different. Git is a distributed version control system, and I know, Mercurial is too, and I thank goodness Git won, because I really didn't want to stand up here and say Mercurial 100 times in 40 minutes. But Git does some things that Mercurial doesn't, but the most important part is the distributed part, which is why Mercurial is almost as good as Git. So this is your project on Subversion, CVS, RCS, any of those centralized version control systems. And whenever Alice saves some changes, then Tom and Marie see them immediately. And more importantly, the continuous integration server sees them immediately, picks them up, does an automated build, runs the automated test, fails, and now everybody's stuff is broken and nobody can work because Alice saved her work too early. Git, the most important thing about Git is that it splits saving your work from sharing your work. So this team with the distributed version control system, Alice can save her work in her local copy of the repository as often as she likes, and then she can share it with the other people when she's darn well ready, when she's sure the build and test works. And that gives us a couple powers. One is that if Alice wants to save her work because she's going to lunch, that is a totally useful reason to save her work. You gotta save it sometime. But she doesn't want to share that information with the rest of her team. They don't need to know what time she went to lunch. So when she saved her work locally, she can actually go back before she changes it and change the history to tell the story of her development in a more meaningful way than when she had the coffee breaks. I don't think you can do that in Mercurial. So that's the piece that makes Git well, one of the pieces that makes Git super special. So when you separate saving your work from sharing your work, you can change the history, rearrange it in iMovie before you upload it to the rest of the team. And another one is getting back to that experimentation. Alice can save her game as many times as she wants in as many different branches, save game slots, as she wants, and nobody else has to know about it. The local repository gives her privacy to experiment. As a bonus, she can also save her work on an airplane or at a conference when the Wi-Fi doesn't work. And as another little side bonus, when this team goes home at the end of the day, they have 4 off-site backups. That can come in handy. All right, so now you know about distributed version control. That's important. Let's move into those math concepts. There's 2 mathy concepts that underlie a lot of the stuff that Git does. And it's important to know the vocabulary words. All right, big letters, DAG. This appears all over those help pages, and at first I was like, the what? But it's really pretty simple in concept. DAG stands for Directed Acyclic Graph. So a graph is anything with nodes and edges connecting the nodes. Directed means that the edges have direction. Those little arrows, they are one-way edges. And acyclic means as long as you follow the arrows, you can never make a circle. That's all. Git uses this in a couple different ways. One, it uses it for the file structure of your project, the directories and the subdirectories and the files in them. And 2, it uses them for the commit graph. And that commit graph is the key to understanding what you're doing when you type a Git command. Next, SHA-1 hash. SHA-1 and hash are both words that appear a lot in the Git documentation, and they're talking about the same thing. So SHA-1 is a particular hashing algorithm, and what a hash algorithm does is it takes a big chunk of content, say all the text in a file, and it runs through like this one-way encryption kind of thing that squishes it down and crams the identity of all that content into 40 hex digits. So this 40-byte hash represents the identity of a file or a commit. And this is one of the terrible things about Git that drives people nuts, because what the heck kind of meaning does this have? And Git uses this as names for commits. Now, it's a little better. You can shorten it, and every commit has a nickname, which is its first 6 or 8 or so, however many bytes it takes to make that unique in your repository. But that doesn't take away the pain of why this meaningless string of characters. So the why is this is a one-way encryption sort of thing. You can't get the file contents back out of this. But what you get from this is identity. It's like a fingerprint. Because if you change 1 semicolon in those file contents, the hash algorithm will produce a completely different string. So any 2 chunks of data, if they have the same hash, these same 40 bytes, they are identical. Technically, there's such a thing as a hash collision. And it could happen that 2 completely different files have the same SHA-1 identifier fingerprint. But it's more likely that you will get hit by a meteor on your way to work tomorrow. And since you're not going to work tomorrow, that's really unlikely. And if that doesn't happen, then trust these to be unique. That's one of the secrets of Git. It uses these all over the place. It uses them for the contents of files, for directory structures, for commits. And I'm going to show you one of those now. All right, so here's the tree. That's another Git word. It means all the files in your project from the root directory on down. So your working directory is where you're manipulating your files. And when you save your changes, this is how Git analyzes your working directory. Start with each file. Here's the contents of this file. Take just the contents, not the name or the properties or the timestamp, just the content. Run it through the SHA-1 hashing algorithm and give it a fingerprint that identifies this file. Then take all the details of what files are in the directory, name, permissions, fingerprint, hash that, and get a fingerprint for the directory. It does that all the way up. And what that means is, when Git is comparing what's currently in your working directory against what's in the repository, all it compares are the fingerprints. It never has to get down into the contents of the file to look at what's different to know whether it changed. All it looks at is those 40 bytes. So that's one thing that makes Git really efficient, is it's comparing strings that are 40 bytes long instead of entire files. It can identify the changes really fast. Another thing that's really handy about this, so Git uses a thing called content addressable storage. Takes the contents of your file, hashes it down to this, and then when it's storing your file in the history, it uses a directory structure based on this. So the fingerprint is also the ID in Git's object database. And what that gives us is, if you ever have two files in completely different places within your repository, or more likely, the exact same contents at multiple places in history, when it goes to store those contents, it'll wind up in the exact same place as before. So you never store duplicate data. You physically can't store the contents twice when they're the same. And a bonus of that is that if you move a file up here to a different directory, it has the same fingerprint, so Git knows immediately that you did a rename. That's really handy. All right, so here we have the combination of a directed acyclic graph with the SHA-1 hash fingerprints used to condense a directory very small and to identify changes very quickly. Now, we're going to go someplace that's one of the most annoying things about Git when you first start using it, and also one of the differences between Git and Mercurial. And people think of this staging area as a burden, as an irritating middle step in saving their work. But I'll tell you why it's useful. Okay, so your changes in Git, and Git thinks of everything in terms of changes, not in terms of files. It's all about the delta. Your changes can be one of three places. Technically four, I'll get to that one in a minute. The working directory is just where you're actually doing your work. And then I used to work for a furniture retailer. So this analogy, the working directory is like the back of the store. And when you want to ship a piece of furniture to another store, you take it off the shelf, whatever, and you've got it in your working directory. And then, next step is you put it on a pallet. And a pallet is this big wooden splintery thing that you put the packages on, and you put all the packages for one store on the pallet. In the video camera, this is your preview screen. This is what's going to be saved. This is what you're taking a picture of right now, the pallet. And it's the staging area in Git. It's also called the index, but the index is a bad word. Staging area is much better. So when you see index, translate that to staging area. So you put the changes that you want to save on the pallet, and then you step back and look at them with Git status and say, is this like a rational, logical commit that I can tell a story about? For instance, are these all parts of the same refactor, or the same rename, or the same bug fix? Do I have both the code and the tests that go with the code in here? And you might have some other changes lying around that are part of a different refactor, or a typo fix, or something like that, and you can leave those hanging out in the back of the store. Okay, so when you're satisfied with that, then you wrap it in plastic, and you put it on a truck. And that truck is the commit. And once it's in a commit, then those changes are safe in the repository and will be retained probably forever. And at that point, it gets a fingerprint that identifies that set of changes as a commit with a particular SHA-1 hash. Quick caveat, there's another place that your changes can be, and that's in untracked files that you haven't told Git to start babysitting yet. Just add them right away, get them into the staging area, because otherwise they do crazy things. Okay, so we use git add to put things into the staging area. Oh, I turned the screen off. Okay. We use git commit to put them onto the truck. You can also go the other way. Reset and then a file will take them out of the staging area. Checkout will take a file out of a commit, really any commit. You can get it out of any commit. A caution about reset and checkout. Here I'm talking about operating on files or paths, which are basically directories and all the files underneath them. They do something completely different when applied to a branch. We may or may not get that later, but watch out. This is some of the inconsistent, confusing interface stuff in Git. Reset and checkout do two totally different things. Okay, but now let's talk about the commit. We've got the stuff on the truck. What goes into the fingerprint that gets written on the side of the truck? Author and author date, that's you and right now. Committer and committer date, that's also you and right now for now. The tree is the fingerprint of the root directory, and in that fingerprint is the identity of every file and the contents of every file underneath it. So that's a whole lot of information in 40 bytes right there. Commit message, you have to put that in. And then the really crucial one, the parent. That's the previous commit, the changes that happened before these changes. And it's a fingerprint of that commit. So the fingerprint of the parent, in your directed acyclic graph here, goes into the fingerprint of the commit. And what that means is when you've got two repositories that are linked and Git is transferring changes between them, as soon as it hits a commit, two commits, one in each repository with the same fingerprint, not only are the contents of all the files the same, but also the entire history of everything that has ever been is the same from there down. So the comparisons stop. This is another way that Git does things really quickly. And it's the beauty of that SHA-1 hash identifier. Yes, it looks ugly at first, but it's really beautiful, see? It contains so much information. All right, so now that we've got a commit, let's get to the really cool part, pointers. So when I started programming, I learned C first, and I'm very grateful for that because I came to really appreciate pointers. Pointers don't take up any space themselves. All they do is point to memory somewhere else that holds information. And it's exactly like that in Git. We have three kinds of pointers. Branches, that's the big one. Master is the default branch, but it's really just a branch, like any other. And all it does, all master consists of, is one file in your .git directory, and that file contains 40 bytes. It points to a commit. That commit is the tip of the branch. Tags are the second kind of pointer, and they're very, very similar to branches. The only difference is they never move. And finally, the special pointer. Head is usually a pointer to a pointer. And head is really important because it represents the current state of your repository. Head points at the branch that is your current branch, and indirectly at the commit that's going to be the parent of your next commit. So sometimes there's an exception to that. Head isn't always a pointer to a pointer. If I said check out this commit, and then checkout does its second thing of doing this, which is move the head pointer. So if I checked out this commit, the head pointer would move down here and would point directly to a commit. That's called detached head state. How many people have gotten into detached head state? Okay, the rest of you haven't used Git very much. Or else you're really careful, because detached state totally happens to me all the time. And the first couple times I saw it, I'm like, oh my God, I'm a chicken with my head cut off. What do I do? But you don't have to panic like the chicken. All it means is that head is pointed to a commit and not to a branch. So the danger of that is the next thing that head does, which is advance the current branch. But first, let's create a new branch. Branchy poo. All right, so here's the thing with Git branches. They're free. They're 40 bytes. They cost you nothing. This is your infinite saved game slots. And you don't know how useful that is until you have it. Running tests, I hardly ever did it. until it was automated, until it was free and run by the server, and I didn't have to worry about it anymore. Branching is the same way. In Subversion, it's the worst. A branch is an entire copy of the repository. And our repository is 7 gigs, which is a problem in itself. But we have Subversion centrally, 7 gig repository, and 5 remote team members who are doing everything over VPN. We do not branch. It's just insanely expensive. And so you get used to working around that and passing patches around and other garbage. Branches are free in Git, infinite save game slots, and they're local, so they're private. You don't have to share them until you want to. All right, so we made the branchy poo branch. Now we can do a checkout of a branch and move the head pointer over here. And then when we do a commit, the head points to the new parent, and it also points to the current branch, which will advance to the new commit. So that's what our new commit does, and it moves our branch. But say now we want to bring these changes into the master branch. We decided, yeah, this is good. All right, so to do that, I do a checkout master. My head pointer moves back over here where master is, and something else happens. All the files in my working directory have been completely changed and rearranged so that they match the files in this tree. Now that's scary to people who are used to Subversion, where they keep separate copies for each branch. But your files in Git are safe as long as your commit is in the history of some branch or tag. That's the only danger of detached head, is if you make a commit from there, you could lose it. All right, but now that we've got the head here, we're going to merge branchy poo and bring in the branchy poo changes. And this is yet another of my favorite things about Git. There's so many. When I merge branchy poo, this is what happens. Boop. All that happens is the pointer moves. There weren't any conflicting changes. All we had to do was zoop, master right up there. And this is called a fast forward merge. So fast forward means when I do the merge, all I do is move the pointer. I don't have to make any new commits. It's just a change to a 40-byte file, super easy. And I think that's really cool conceptually, the way Git treats pointers, and it can just move them around. Incidentally, moving around pointers, checkout does that when it moves your head pointer, and reset can move your current branch pointer too. That's the second weird thing reset does. Okay, but what if we did have concurrent changes? If we also had changes that we made on the master branch, and now we want to bring the branchy poo changes in, we type git merge, and something completely different happens. We get a merge commit. The git merge creates a new commit, and the whole purpose of this commit is to contain these changes and branchy poo changes, so it has 2 parents. And now we get into a graph being different from the straight line tree that we have in Subversion. And then whoop, the master pointer moves up to point at the merge commit. Branchy poo, he hangs out where he is, and you can delete him when you feel like it, because these changes are now safe. They will never go away because they're in the history of this branch pointer. All right, so now we know one way to bring our changes into master branch. But the interesting part about Git is that you have choices. But before we talk about the next choices, we're going to go ahead and add some other people to our team. And we're going to start talking about that central repository, which in Git, really all repositories are created equal, but just like all people are created equal and somebody has to be president, we pick a repository and we name it origin. That's the default. Usually we use a bare repository for this. That's an option for repository setup, and it means it doesn't have a head pointer. Nobody commits directly to origin. What they do is clone it. And when I clone this repository, this is origin now, and this is my repository, I got a copy of all the history in it. And I also got a remote. My repo knows about a remote named origin that points over here. And what I get from that is a branch. My master branch now has an upstream. And the upstream means the purpose of my master is to work with this master. and exchange commits between it. So I also get an origin master pointer, and this one tracks this one directly and is always pointing to where the last place I knew this one was. So somebody else put some changes in the repo, and I pull those over. Nope, oh shoot, I used the bad word. So a lot of people will tell you to get the changes of other people, you use get pull. I think get pull is bad. Pull does a fetch and an automatic merge. To get other people's changes, use get fetch. And what fetch does, so this origin's master branch has moved up here now, and when I do get fetch origin master, it pulls everything up from the remote repository and moves my origin master pointer, but that's all it does. I'm still here, my head is still right here, and I can then go do a diff here, I can find out what's going on, I can look at what other people have done before I decide to bring it into my working directory. And then when I do, I might get merge conflicts, and then I can resolve those. I don't have time here to tell you what to do about merge conflicts, but I want to tell you one thing not to do. When you type git merge and you have conflicts, it leaves your repository in a really crazy state. So what you don't want to do is get up from your desk. Do not pass go, do not eat lunch, do not go to the bathroom until you have either reserved the merge conflicts or done a git merge abort to put your repository back where it was before. Then you can go to the bathroom. Then you can come back and decide what you want to do next. Okay, then when you're ready, you can do a push to share your changes. And what that does is take all the stuff in your master's history, copy it over to origin, and then do a fast forward merge on the master pointer in the origin repository. And the remote repository, by default in this setup, will only do a fast forward merge. So if you get an error message that says, I couldn't fast forward, that's why. There were some other changes, you have to bring them in, resolve the conflicts, and then push so that it can do a fast forward. Move the pointer. Okay. So now I told you I love feature branches, and I do. And one reason that I love them is because if I'm over here on a branch and I'm doing my feature work, I can always check out master and do a bug fix. There's also git stash for changes you haven't committed yet. It's an option. I prefer to make a commit. All right, so let's talk about getting this feature branch and this bug fix back in. In this case, I wish I had my bug fix in my branch. In fact, what I really wish is that I had done this bug fix before I started the branch. Rebase lets me pretend that's how it happened. So when I'm on this branch over here, and I do git rebase master, I get a copy of each commit. It takes the changes from here, applies them here, and also with every other commit in there. And then my branch is up there, and it looks like I did this bug fix first. That's what rebase does. You have choices. You can use merge or rebase to bring in other people's changes. My personal preference is rebase. And then the author and author date is the same, but the committer and the commit date change. So you get both pieces of history. This commit was rebased on this date. It was originally made on this date. There's a few more fun things. I really like cherry pick. This is when I've made a change in that branch, and I wish I had that over in master, and I can pull over that one commit, cherry pick, and then the secret name of the fingerprint of this commit, and it comes over here. Later on, I might choose to squash. That's another fun way to combine your changes. And a merge squash takes all the changes, but not the ones that are already there. It's smart that way, and puts them in one commit. So it's another way to not get a merge commit. All right, so there's a lot of other insanity you can do with Git. Rebase -I. Oh, that was a picture of merging two repositories and to pretend they've always been one. I actually did that once. Rebase -I, some people consider insane. I consider awesome, but I don't have time to tell you about it. Dang it, it's really cool. This is what you can do. You can change your history and tell your story. And you should totally tell your story. You get to decide how. For tools, please get something with a picture of the commit graph. It doesn't matter what, so you can look at the commit graph, type your spell, and go back and see if it did what you want. Thanks, I'm Jessitron, Git happens, and there's some resources on this website here. I think we officially have 4 minutes for questions.
Yes, so once again, if you'd like to ask a question, just come up here to the mic.
I'll also be around for the rest of the conference, and I get really excited when people ask me questions about Git, so please approach me at any time.
Yeah, I'll ask you a quick question. When I often get the feeling of like, oh, and I'm kind of scared. Like, what's your go-to, like, what's happening sort of tactics?
Excellent question. So step 1 is look at the commit graph. If you're uncertain what's going on, open the commit graph. There's a really long git log command. You can have it printed out in ASCII art, but I'll usually go to git k is the GUI that comes with Git. It's really crappy, but it's always there and it works. Or source tree or my IDE. IntelliJ has a good plugin. Something to see the picture of where all the branch pointers are and what commit is where. Another really good trick is git reflog. And you can remember this because the first time I saw it, I thought it was reflog, which is what I wanted to do to myself when I got in that situation. So git reflog is a different sort of history. It shows you the history of everywhere your head pointer has been. So if you want to make the last 20 minutes like not have happened, Git is so weird. You can even say, reset my repository to the point where head was 20 minutes ago. Literally, 20 minutes ago. And so you can always get back to someplace you were before. I'm always nervous when somebody starts a question in Git about Git with, so I was in the middle of a rebase. And those are even worse than the merge conflicts when you stop in the middle. And that's like Git's version of, it was a dark and stormy night. Yeah, so the reflog is helpful and the commit graph. Anything else? I hope you're all saving your questions up to ask me later. I promise I'll jump up and down if you do. Thank you very much.